Alright, here's this week's past HSC question that I've set you for homework, 1997, question 2, complex numbers. So the first one was to express in mod arg form and then hence to evaluate this. So expressing that in mod arg form is the modulus of root 3 minus I is simply equal to the square root of root 3 squared plus 1 squared. X squared plus y squared, which in this case turns out to be 2. And to get the argument is the theta, and so tan of theta is equal to y on x. In this case, I'm going to take it as 1 on root 3. Give me theta is equal to pi on 6. But what I need to be careful is when I'm doing these questions is that I'm making sure I know where root 3 minus 1 is. So if I plot the complex number root 3 minus I right there, I can see it's in the fourth quadrant. So my argument's actually negative pi on 6. So I can actually express now root 3 minus 1 in mod arg form as cos I sine negative pi on 6. And that should be 2 because the modulus was 2. 2 cos I sine negative pi on 6. Okay, part 2. Hence evaluate root 3 minus I to the 6. So we'll just use de Moivre's theorem. And for part 2 we'll get that's 2 to the 6 cos I sine negative 6 pi on 6. Which I can see is 64 cos I sine of negative pi. That's the same as the cos of pi as well, cos I sine pi. And if I work that out, I can see that 64 cos of negative pi, cos of negative pi is negative 1, gives me negative 64. Sine of negative pi is 0, so I simply get equals negative 64. Okay, moving on. Part B. Simplify negative 2i cubed. So if I want to do that, I get negative 2i cubed is equal to negative 8 times I squared times I. Remembering I squared is negative 1, so it's something simpler for me to put in there. So I get 8i. Hence is an important word. Use what you've just done. Hence, find all complex numbers z. So z cubed equals 8i. Well, if z cubed equals 8i, then z equals negative 2i is a solution. And so if it's a solution, then what I can do is I can find the other solutions by plotting negative 2 down here. And then all other solutions will be equally spaced around a circle of radius 2. So there's going to be 3 solutions in total. So it's going to be 2 pi on 3 and 2 pi on 3 this way. And that'll give me my other 2 solutions of radius on this circle. Oops, sorry, not doing that very well, am I? So it'll be 2 pi on 3 away from negative 2 and 2 pi on 3 away from negative 2 around these 2 directions to divide that circle equally into 3 spaces. So that would mean this angle in here is going to be pi on 6. So this will be 2 cos I sine pi on 6. Similarly, this angle over here will be pi on 6. That'll make this full angle around here 5 pi on 6. So I'll get this as 2 cos I sine 5 pi on 6. So I've got my 3 solutions. It says to express in the form x plus iy. So far my 3 solutions are z1 is equal to negative 2i. My second solution, 2 cos I sine pi on 6. And my third solution, 2 cos I sine 5 pi on 6. So if I work through them, that's already in x plus iy form. This one gives me cos of pi on 6 is root 3 on 2, and sine of pi on 6 is a half. So when I multiply both of them by 2, I end up with root 3 plus I. Similar results over here, except cos will be negative, so it'll be negative root 3 plus I. Part C, sketch the region where these inequalities both hold. This one here, what we did last time round. We saw that I could write this as z minus 3 minus I less than or equal to 5. And so I can say that's a circle. The centre is 3, negative 1, and radius is equal to 5. This one here, it's saying the distance away from 1 and distance away from negative 1 must be the same. That would have to imply that it's got something to do with the y-axis. So let's have a quick look at it in algebraic form. And so we've got, putting in x plus iy, we've got x plus 1 as the real part plus iy is less than or equal to x minus 1 plus iy. Applying the modulus formula on both sides means that you get x plus 1 all squared plus y squared must be less than or equal to x minus 1 all squared plus y squared. Obviously having squared both sides. Expanding that out would get rid of the x squareds and a little bit extra, leaving with just 2x is less than or equal to negative 2x, 4x less than or equal to 0, x is less than or equal to 0 would be the solution or the region here. And I want both of these to hold. So what I want is I want a circle. Centre is 3 and negative 1. Radius is 5. I've drawn this way too big. So we might just rescale our 3 and negative 1 here, I think. It says 3, negative 1, that's my centre. Radius from here is 5. And I want the area inside that, but I also only want the area that's less than or equal to 0. So I just want this area over here for both of those regions to hold. Okay. Last question. W equal this and Z equal this number. The modulus of W is equal to the modulus of Z, and they're both 1. Find WZ and WZ bar in the form x plus I. Y. So WZ is going to be the product of these two, and when you multiply these two together you're going to get 15 minus 48 plus 20I plus 36I, and 5 times 13 is 65. And so if you work that out, you're going to end up with negative 33 plus 56I all over 65. Okay, WZ bar is going to be very similar, except for Z bar you're going to have a negative here. So you're going to get the same numbers, just change a few signs around. You're going to get 15 plus 48 plus 20I minus 36I, and again all over 65. And when you add that, you get 65 minus 16I all over 65. So that's quite mechanical, just doing the expansion of the product. Part 2 is an interesting one. It says, hence find 2 distinct ways of writing 65 squared as the sum a squared plus b squared. Right. So what we need to be thinking about here is that how can we get a squared plus b squared? Now a squared plus b squared comes about by multiplying a complex number by its conjugate. So in other words, if I took w and multiplied by w bar, then what I was going to get, I would get x squared plus y squared. And that would be equal to the modulus of w all squared, which is simply equal to 1. And that can be quite useful to us. So therefore, if I take wz and multiply by wz bar, I'm going to get wz times, now w bar z bar when I separate them out. And that's going to be equal to w times w bar times z bar. And from what I just set up here, when we multiply these, x squared plus y squared, we're going to get the modulus squared, and earlier in the question we're told the modulus was 1, so 1 squared is 1. So this is simply going to equal 1. So if I go back to the original question, I'm going to get, go back to what I worked out before. My WZ was negative 33 plus 56i over 65 multiplied by its conjugate, negative 33 minus 56i on 65. I'm going to get 1 when I multiply that. And across the bottom I've got 65 squared, bring it to the other side, equals 65 squared. And when I do this, I get x squared plus y squared, so I get 33 squared plus 56 squared is equal to 65 squared. Similarly, wz bar times wz bar, the conjugate of all of that, must also equal 1. And so therefore you're going to get the same sort of result coming out. I should have said 63 earlier, my apologies, 63. So you're going to get 63 squared plus 16 squared is equal to 65 squared. So I've managed to actually write 65 squared as two distinct ways, sum of two squares.